In this video, we're going to look at a way that you can calculate the rate law order for any of the reactants that appear from a table of data. And the reason that we're talking about this, the way that we went through it in the previous video was more of an intuitive, still math-based, but not just a direct calculation. And that works really well for a lot of people, but it does not work well for everyone. So this is a really great method to use if that intuitive stuff doesn't stick in your brain right. It's also a really great way to error-proof your determination of the rate law order, or for non-obvious cases. So the rate values that we were working with in the previous cases were easy to look at and see that the values had been doubled or quadrupled. In this case, you can probably look at it and see the same. But when we have real experimental data, it might not be as obvious as it was in those two cases. So what you will do is choose two trials, and it can be any two trials, and then you will mathematically write the division of one over the other to look at the relationship between the two trials. And we're going to include everything from the rate law in this. So the rate of, I guess I can use A and B here. So A and B, it can be any two trials, and you can put whichever one in the top you want, whichever one in the bottom you want. So rate for reaction trial A is going to be equal to the rate constant. And we're going generic here, so concentration of A to the M power, concentration of B to the N power. This is just the rate law will take this form for whatever we're working with. And then divide by the rate law for the second trial, so we'll call it trial B, which is equal to the rate constant times the concentration of A to the M power times the concentration of B to the N power. All right, so this is, let's put a little highlight box around it. This is what our strategy looks like. And as you can see, we have a reaction and a table of data. And our table of data has two reactants in it, so we are going to get orders for both of those things. So let's just pick some trials. So I have picked trials 1 and 2 for the first ones to look at. And if I write this out, so we're going to compare trials 1 and 2. I have done it as trial 2 over trial 1. You can do it the other way. You should still get the same answer, which would be a great way for you to practice and confirm that that's the case. So for trial 2, my rate of reaction is 0.0082 molarity per second. For trial 1, my rate is 0.0021 molarity per second. And this is equal to the rate law for trial 2, so the rate constant times the concentration of my first reactant, which is NO2, which, make sure I get this in the right order. I'm doing trial 2 over trial 1. NO2 has a concentration of 0.20 molar to the M power. I don't know what that power is, but I'm going to find it. Times CO, which has a concentration of 0.10 molar to the N power. And then for trial 1, it's a rate constant. My NO2 concentration is 0.1, and my CO concentration is also 0.1. All right, so I can cancel a whole bunch of stuff out. Let's do this in orange. So the rate constant, it's a constant, it's the same number, so K divided by K is 1. 0.1 to the N power divided by 0.1 to the N power is 1. And I think that's everything I can cancel outright. So now I can just do some of the actual math, right? So the 0.0082 divided by 0.0021, I get 3.9. We're going to round this to 4. And that's equal to, my 0.2 to the m divided by 0.1 to the m, I can combine the 0.2 over 0.1 inside parentheses and just keep one of those powers since that power is the same. So what I'm actually solving is 4 equals 2 to the m power. So you could probably solve this without doing anything else, right? So 2 to the second power is 4, so m equals 2. You can, if it's anything more complicated than our basic orders or most common orders, you could take the log of both sides, right? There's a method to getting something out of a power that we have used a couple of times in acid-base chemistry. You could apply that here if that is something that you would prefer to do. So I know now that my reaction is second order in NO2. So we can probably by inspection figure this one out for the CO, but we can also do this calculation a second time to figure out what the CO dependency is. So let's find 2 trials where the NO stays the same. So the only ones that I see are 2 and 3, and my CO changes. Now you can look over here at the rate. My rate doesn't change when I change CO, so I'm expecting a 0 order dependency. But we can set this up, and I have mine as trial 3 divided by trial 2. Again, you could do 2 over 3 if you prefer. And it's 0.0082 molarity per second, 0.0082 molarity per second equals the rate constant for trial 3 times 0.20, and we can put the second power in here, or we could put an m. It's going to cancel out either way, times 0.20 to the n power divided by the rate constant, 0.20 to the 2 power times 0.10 to the n power. So I can cancel the constants, and I can cancel 0.2 to the second power. And what I am left with is 0.0082 divided by 0.0082. So 1 equals 0.2 over 0.1, which is 2. I think. I hope I did that right. Yeah, I did. To the n power. So the only way that 1 can be equal to any number that's not 1 to a power is if n is equal to 0. So now that I have my orders, I still have to put them together to write the full official rate law for this reaction. And it is NO, is it NO or NO2? NO2 to the second power, and CO to the 0 power. So we're not actually going to write that in here. So it's just the rate, and you just write out this entire word when you're reporting the answer, is equal to the rate constant times the concentration of NO2 squared. So this is a mathematical way that you can calculate the rate law order for any of the components of a reaction. Now that we have this, now that we have an actual rate law for a real reaction, you can calculate the rate constant. So that is what we're going to end this video with, is talking about rate constants. And what we will do is pick any trial. Now, obviously, when you are doing this in lab, or if you were doing this in a real research setting, you would calculate the rate constant for every trial and then average them and calculate error and all of that fun stuff. For us, we can get by with just picking any trial. What I want you to get out of this mostly are the units on the rate constant. So let's use our previous example. We have the rate law, which is that it's the rate constant times the concentration of NO2 squared. So if I just rearrange this, I can calculate the rate constant if I take the rate and divide it by the concentration of NO2 squared. And I have that information. So pick any trial that you want, and you should get a number close to this. It looks like I picked trial 1. My rate was 0.0021 molarity per second, and my concentration was 0.10 molar, and I'm going to square that. So my value is 0.21, and my units are 1 over molarity times seconds. You're like, those units are nuts. Those units are vital to this setup. So every rate is in molarity per second, regardless of the dependency. So the units on your rate constant are what counterbalance those dependencies in order to make your rate a consistent value. Well, a consistent unit value. So, well, I already said this, but we'll write it again. The rate is always in molarity per second. So the units of the rate constant depend on the order. So for something that is 0 order, K will have units of molarity per second. For something that is first order, K will have units of 1 over seconds. And then second order, which we've just seen, K will have 1 over molarity times seconds, and so on. And this is in relation to the overall order. So if you had something that was second order in reactant A and first order in reactant B, that's third order overall. Your rate constant units need to reflect that and make sure that your rate that you get always has units of molarity per second.